my name is Kelsey Wright. I am a neuroscience PhD student in Jun Yao's lab at Northwestern, and today I'm going to be telling you about my research, how two areas of the brain communicate with each other to control movement. Have you ever been minding your own business, maybe you're really focused on something and somebody comes up and unexpectedly taps you on the shoulder and you respond like this? You jump, you flinch, you might even drop what you're holding, but how many of you wanted to do that? Probably none of you. Your brain just does it. It makes you move on its own. So how does it do that? Well, we're going to discover that together through this presentation, but first I want to talk to you about the two areas of the brain we're going to talk about today. First is the cortex. The cortex is the outermost layer of the brain. It controls very high-level thinking, and today we're going to be talking about how it controls very precise movements, things like writing your name or playing an instrument. It also controls your permission to move. The next thing we're going to talk about is the brainstem. The brainstem is located very deep in your brain underneath everything else, and it controls a lot more basic things. In terms of movement, it controls your posture. Think about leaning from one side to the other, and it also controls larger movements, things like moving your whole arm. These two areas of the brain work together to control a majority of your movement. Think about taking a drink from a mug. You have to reach out, grab it with your hand, lift it to your mouth, all in one smooth, coordinated movement. We know that the cortex talks to the hand, the brainstem talks to the arm, but these areas also talk to each other. However, scientists don't actually know what these two areas are saying to each other. We know that they talk to each other, we can see that they're connected, and the reason we don't know what they're saying to each other is because for a very long time, science has studied these two areas separately. So if we know that these two areas are important to each other in controlling movement, why have scientists studied them separately for so long? In order to answer this question, we first have to ask, how do we even study the brain? One way to study the brain is using electrodes. Electrodes are like tiny microphones that sit on the surface of your scalp, and they can listen to what your brain is doing through your scalp. It's kind of like pressing your ear up to a door to hear what's being said on the other side. And electrodes, because they're located on the outside of your scalp, are really good at hearing what the outer layer of your brain is doing. And as we all know, the outer layer of your brain is your cortex. So electrodes are really good at listening to what the cortex is doing and give us a really great picture of that. However, they're not so good at looking at what the brainstem is doing. The brainstem is located so deep in your brain, it would be like putting your ear up to a door and try and hear what's happening 3 or 4 rooms over. So if we can't use electrodes to look at the brainstem, how do we look at the brainstem? Well, one of the ways we've learned about how the brainstem controls movement is by looking at people who have had stroke. When somebody has a stroke, their cortex is often damaged, and they can no longer perform those really precise movements, things like writing their name or opening their hand. When the cortex is damaged, all that's left is the brainstem to control movement. So we can learn about how the brainstem controls movement by looking at the movement that is remaining after somebody has a stroke. So you can probably see why scientists have studied these two areas separately for so long. We can't use electrodes because they only look at the cortex, and we can't use people who have a stroke because there's no cortex to look at. So how do we study these two areas together? It's by startling people. So it turns out that this movement is controlled entirely by your brainstem, and that's why you move without your permission, because your cortex isn't involved at all. It's all controlled by your brainstem. So we startle people in the lab using a really loud sound. It's about the intensity of a fire alarm. So let me explain to you how this really loud sound causes your brainstem to make you move. When you hear a normal sound, it comes in through your ear passes it to your brainstem passes it up to your cortex takes its time, makes a decision, thinks about what to do, and then your cortex and your brainstem work together to perform a movement. In this case, you might wave back by lifting your arm and moving your hand. But when you hear a really loud sound, your brain thinks it's an emergency, and there's no time to go all the way to the cortex. You have to act now, and so the brainstem causes you to move. We think that the reason you flinch or jump is to protect yourself from the oncoming attack, even if it might just be your friend tapping your shoulder. So this is how we study your brain in the lab. Sort of. There's actually two kinds of startle. The one we've been talking about so far, where you're unsuspecting and you're suddenly scared, is called the classic startle, but the one we use in the lab is called startle react. A really good example of startle react is runners at a starting line. When you're preparing for a race, a really loud sound goes off like a gun in order to signal the start of the race, but you don't see runners tripping all over the place or flinching at the starting line. They take off running. So what is the difference between these two kinds of startle? Well, it turns out that if you're concentrating really hard on what movement you're going to prepare next, and then you're startled by a really loud sound, instead of flinching or jumping, you'll perform that movement. And the first little bit of that movement, that first step, is going to all be controlled by the brainstem. So by combining electrodes to study the cortex with the startle to study the brainstem, we can look at how these two areas communicate to control movement. I can ask people in the lab to perform movements like lifting their arm, opening their hand, or performing both together to see how these two areas work together to control a complex movement. And it's really cool that we're able to see this for the first time, but why do we care that the brainstem and the cortex talk to each other? Why does it matter? And more importantly, who is this helping? And hopefully, it'll be helping people who have had stroke. Right now, the recovery for stroke is mostly physical and occupational therapy, and those target having people who have had strokes be able to perform everyday movements with less movement than they're used to. But it doesn't really target the recovery of that cortical area or the brain. And we're hoping that's where my research can come in. If we know how the cortex and the brain talk to each other, it's possible that we can develop therapies that target this communication, or even devices that replace this communication. So in addition to my research finally allowing us to see how the cortex and the brainstem communicate, it's also going to help people who have a variety of movement disorders. My name is Kelsey, and thank you for listening to my talk about how the cortex and the brainstem talk.